60 years ago, Frank Drake, Carl Sagan, and a handful of other scholars gathered at the request of the National Science Foundation to discuss the scientific merits of SETI, the search for extraterrestrial intelligence. Could a case be made to look for life and for intelligence beyond Earth? And if so, what were the crucial parameters? It was Frank's job to craft the agenda for the meeting, and as he thought about how to organize the discussions, he ended up sketching out the key scientific questions he'd need to answer if he were going to figure out how common alien technology is in the Milky Way galaxy. These were questions like, what is the birth rate of sun-like stars? What fraction of those stars have planets? How many of those worlds might be habitable, at least by our standards? And what fraction of those habitable worlds might go on to develop life, intelligent species, and ultimately, detectable technologies? Perhaps most importantly, he felt, was the question of how long civilizations would remain detectable before they evolved beyond their noisy technologies or disappeared altogether. Frank realized that his list of questions could be expressed as a series of independent variables, and that if those variables were multiplied together, they'd produce the number of detectable technological civilizations in our own galaxy. His formula soon became known as the Drake equation, and today it is among the most famous and recognizable equations in all of science, perhaps second only to Einstein's E equals mc squared. The Drake equation now serves as a roadmap for the field of astrobiology, the study of life in the universe, as well as life's origins here on our home planet. And so, not surprisingly, the single most important laboratory we have for astrobiology is Earth. But just as planet Earth informs the study of alien life, so too does astrobiology inform a better understanding of life here, how it began, the conditions necessary for life forms to evolve and thrive, and the consequences of Earth's most advanced species on its long-term habitability. The last variable in the Drake equation is represented by the letter L, which signifies the longevity of detectable civilizations. L is arguably the most intriguing and the most vexing of the variables in the Drake equation. Today, we explore the topic of climate change through the lens of astrobiology and planetary science. Can these fields offer important perspectives on a crisis that is testing our own L variable? Can examining climate change at a planetary scale bring greater awareness to the magnitude of this challenge? And might that help accelerate more decisive action? These are the questions we seek to address today. Welcome, everybody. I am Nadia Drake. I'm a contributing writer with National Geographic, and I'm also related to the Drake of the Drake equation, who happens to be my father, Frank. As the video said, this panel is on the L variable, which is the last variable in the equation. It's the one that asks us to think about how long, on average, technological civilizations remain detectable. Dad says that L is the most vexing variable in the equation, and it's the one that's the least knowable in advance, meaning that it's tough to reason your way to an answer without any data points. There are actually many intricacies and nuances that go into the L variable, including the issue of who's asking the question and what kinds of detection capabilities they have. But for now, I think we can keep it simple and consider humanity's L, the longevity of our own technosignatures, and the factors such as climate change that affect that longevity, as well as what that means more broadly for us as a civilization. So we have three panelists, each of whom appear to be on other worlds, and each of whom will briefly introduce their perspective on the L variable and what it means for humanity. Mike Wong is an astrobiologist and postdoctoral fellow at the Carnegie Institution for Science. Anne-Marie Cody is an astronomer at the SETI Institute. And Nathalie Cabrol is an astrobiologist and director of the SETI Institute's Carl Sagan Center for the Study of Life in the Universe. Toward the end of the hour, we will be taking questions from the audience, so please do put those in the Q&A that's at the bottom of the Zoom screen. And okay, Mike, you are up now.
Hi, yeah, so people who know me well know that I'm, in addition to being a scientist, a really big Star Trek fan. So I'll begin by setting the stage by showing this slide that I generally show when I give public science talks. And when I tell the story of how ever since Star Trek's inception, the creator of the show, Gene Roddenberry, wanted science to be at its core. So he actually wrote about the Drake equation in his 1964 proposal to NBC Studios for his new science fiction show concept. And that's what you see on the top line there. Thing is, in 1964, you couldn't just Google what Drake's equation was. And Gene Roddenberry, in fact, had no idea what Drake's equation looked like. So under the time pressure of the studio to submit his proposal on time, he just scribbled something random on a piece of paper and sent it in. And that's what you see on the bottom line here. It's an absolutely nonsensical equation. Luckily, the studio had no idea what Drake's equation looked like either, and Star Trek was accepted and approved. Now, many years later, Professor Drake actually came aboard the set of Star Trek, I believe Star Trek Voyager, as a technical consultant. And when he was on the set, he was shown this fake Drake equation that Gene Roddenberry had penned in his name. And when he saw it, he just laughed and he said, "Oh, Gene, don't you know that raising something to the first power is simply itself? Like, why would you do that?" So I'm an astrobiologist, and all of the terms in the Drake equation are really intriguing to me. The ones that I think about the most in my work are probably N sub E, so the number of Earth-like or the number of habitable planets out there. Today, we have the understanding that to be habitable is not necessarily to be exactly Earth-like. You can potentially be habitable as an icy ocean world like Europa, or with a completely different atmosphere from Earth like Titan, or indeed the early Earth. And I also like thinking about F sub L. So that's the fraction of planets in which life emerges. So the origin of life, which is a huge open question in our field. Needless to say, the further you go down to the right-hand side of this equation, the more speculative you get. So I really look forward to speculating with you all about the nature of the L variable. But just to bring things full circle for my opening remarks here, people say that science fiction is at its best when it uses faraway worlds and fanciful adventures to talk about issues that are very real and very close to home. And I think the same is true of astrobiology. We can't ask about the origin of life without asking, what is life? What are we? And we can't talk about the habitability of other worlds without considering how we are altering the habitability of our own. And we can't think about exploring the cosmos without remembering how our ancestors explored this globe, oftentimes for greed and exploitation and colonization and domination. So, this is a wonderful paradox that looking outwards and towards the future also means looking inwards at our own selves and our history on this planet. And I think it's this paradox that brings us all together today for the fascinating discussions that we'll have.
Thank you so much, Mike. Anne-Marie. I think you're going to have to unmute. Yes.
Okay, I'm unmuted now. Thank you.
Yes.
Let me share this. Perfect. Oh. Okay, so I'm an astronomer at the SETI Institute, and oh, that's still not coming on. Sorry about that, guys. Okay, here we go. I'm an astronomer at the SETI Institute, and I too have been involved with search for planets around other stars, and I'm very interested in what we're going to find in terms of life that's out there. And the question when we come to this L variable that has already been mentioned is, are we going to find advanced life? Most of the astronomical technology being used today is focused on finding molecular signatures, things that could be any form of life, from single-celled organisms to something very advanced. And so one question that intrigues me and many other scientists at SETI who have been using radio telescopes to search for signals of life, signs of life elsewhere for decades, is how would we find something very advanced? And one schematic that can offer guidance is shown here. This is a hypothetical idea of what would happen when civilizations and such as ours on Earth evolve past the energy capabilities of their home planet. We use a certain amount of energy here on Earth now, And if we extrapolate far into the future, eventually we will exceed what is available to us. And so this idea by Kardashev some decades ago shows that perhaps very advanced civilizations beyond us might actually build structures around their host stars to harvest energy and send it back to their planet. Eventually, there may be something on a whole galaxy scale. As an astronomer, I've been using space telescopes for the past decade to monitor the brightness of stars out there. These space telescopes are many of the telescopes that have been used to find planets around other stars, but we can do other things too. And specifically, if there are structures in orbit around other stars that are being used for energy purposes or even communication, we might actually be able to detect those as they pass in front of the parent star. And so that's what's shown on the bottom here. The brightness of the star may fluctuate in time in a way that does not match with known astrophysical phenomenon. So that's actually what I'm working on right now using space telescopes. Here is the Transiting Exoplanet Survey Satellite, or TESS for short, to look at literally tens of millions of stars to see if we can find any signs of a very advanced civilization. Will we find something? Time will tell. And this is just going to be very exciting. If we don't find anything, what will that mean in terms of the survival of life elsewhere in the galaxy? That may be interesting as well. Thank you.
Thank you, Anne-Marie. I agree that both outcomes of that search are equally intriguing. And I think we will get there in the discussion in a bit. But first, Nathalie.
Good morning, Nadia. It's a great pleasure to be here. I am an astrobiologist, as you say, so very much like Sarah Johnson introducing herself, I am interested by the development of life and the survival of life on other planets. And I am doing a lot of field work in terrestrial analogs, which means that I'm trying to understand what kind of habitability, what kind of habitats, and also what kind of life is surviving in environments that are analogous to those that we're finding in the solar system. And so the parameter of the Drake equation I am really interested in, of course, are the ones with the origins of life and the one that relate to habitability. But what I'd like to say about the L factor, and this is for my other hat, the one from the director of the Carl Sagan Center. There is the empirical side of me and the theoretical side of me. I like to question questions. And the L factor in the Drake equation is everywhere. From the time when life appears on this planet, species are going to meet their L factor. But what is really fascinating about ours is that throughout the evolution, we have a natural course of coevolution of life and environment, which means that, well, species adapt or disappear, right? But today, we are really the first species who is capable of altering that course. And we have a really important impact on, our own duration, the environment that's favorable to us. So these are really the aspects of the Drake equation that I'm fascinated about. And I really hope that we are going to talk about that today.
We will definitely talk about that. Thank you all. I really appreciate it. I guess the first question, just to kind of set the groundwork for the rest of the discussion, is when we think about humanity's L, the length of time for which we have been detectable, what is the answer to that question now? What are we thinking about our longevity as a detectable civilization? And what are some of the factors that can have an impact on that? And this is for the entire panel, so whoever wants to jump in.
Okay, so probably go after it. In terms of humanity, life actually, well, before the humanity, I mean, life in itself has a footprint on this planet. And it started really, our first visibility as a planet that was alive is really with a change in the composition of our atmosphere. That's 2 billion years ago. all of a sudden life transforms everything. And maybe there is a message there already, because it's already a complete disaster, ecological disaster that kills about all of the life that's there. So maybe we inherited that ability to actually kill life by transforming ourselves. But the L factor of whatever life was before that time all of a sudden became very short. As far as humanity comes, definitely the beginning of the industrial era is where things started to change and accelerate. Bill mentioned that a little bit earlier on about the impact of the industrial times. What is really interesting, and I'd like us and the panel in general to come back to that notion, which is critical for the L factor, is all of a sudden this awareness that we are in the system. So for the longest time, there were fewer humans in the first place, and we were working with the planet. Whereas now we are putting into this system other things, you know, whatever gas we are putting into. And for the longest time, we didn't realize that there was any impact to it. But the problem with the system is there are feedback mechanism, and they are going to come back. And the more you put in, the more at some point they are going to show up. And this is what's happening now. The issue for our L factor is that all of a sudden, the increment is not linear anymore. It starts to become exponential. And this is what we are seeing right now. So the L factor is, our duration is reducing by the year at this point in time. There is no norm to the change in the environment that we are seeing. Next year is not going to be like this year. The change is exponential.
Yeah, I think it's interesting because when I first started writing about the Drake equation, you know, we would say things like humanity has been detectable for somewhere on the order of a century, you know, since military radar started squawking quite loudly at the beginning of the 1900s. But then when you do consider that we are a species that has the capability to change our environment in observable ways, I think we can start to consider that RL, we've been detectable for much longer than we think, again, beginning with the Industrial Revolution. And so, Mike, I'm curious because I know that you're working with biosignatures and thinking about what biosignatures might look like on other planets. What are your thoughts here? I saw you nodding quite a bit as Nathalie was talking.
Yeah, that's just because I thought Nathalie's answer was so brilliant and really encompassing of the whole problem of, you know, how we think about L. It definitely is very tied into who we're thinking about is observing us, right? Because depending on their telescopic technology, they may be sensitive to trace gases in our atmosphere, or they may be even able to observe changes over time in our atmosphere, or even look at Earth's surface and understand that life has been present due to photosynthetic pigments on our surface, and then even see like the impact of humanity spreading across our world. I think maybe the only other thing that I would add to this is that oftentimes, you know, we think about L as a single number in the Drake equation, right? But I think that to me, what L represents is sort of just a statistical function, the way that we would think of maybe how temperature relates to the kinetic velocity of gases in our room. You can assign one single number to the temperature of the air in the room that you're in right now, but that represents a whole distribution of different velocities. And maybe the deeper question is, I mean, obviously humanity's L really matters to all of us on a personal level, but maybe the deeper question, cosmologically speaking, is, you know, what is the distribution of L? And what is its shape? What is its peak? How narrow or spread out is it? And perhaps the biggest question of all is, can we derive what that should be using the laws of nature, the way that you can derive the Maxwell-Boltzmann distribution of the velocity of gas molecules from first principles? So that's obviously a big open question, but it's something that I think is worth thinking about.
I was thinking about that in the context of the megastructures that Anne-Marie mentioned that she's looking for. And so I know we kind of teased at the fact that if you find evidence for some of those megastructures, it will obviously be transformative. But the other side of that coin is, what if you don't find anything at all? What does that mean? And does it actually tell us something informative about longevity, about surviving the path that we're on right now?
Yeah, I think it's a really interesting question. If we look at 100 million stars and we don't find anything, it's not necessarily a nail in the coffin that there's nothing out there. It's we're still limited by humans' imagination and where we think our own civilization is going. You know, we're consuming energy at a rapid rate, but it's possible that civilizations become much more efficient, that they realize that they never need to build such structures. We're certainly nowhere near having the capabilities of doing that ourselves. So in that sense, if other beings in the galaxy are looking for structures around our sun, well, they wouldn't find any, even though we're here and we might argue we're somewhat technologically advanced. So right now, I think we'd just be detectable possibly at radio wavelengths for a few decades. And the other thing one needs to keep in mind is, you know, assuming we understand basic physics, you know, there's sort of some signal travel time. So if there's a civilization all the way on our other side of a galaxy, it's going to take thousands of years for either us to detect their technology or them to detect us, simply because light doesn't travel instantaneously. So it's going to be interesting to see, you know, especially with the projects that I'm involved in, you know, we're probably most likely not to find anything, but ultimately we're going to figure out exactly what that limit tells us about, you know, could there still be stars with megastructures, and we just didn't look at enough.
Yeah, it's totally fair. I think it's interesting that when we talk about L, I think there's this assumption, and maybe this is just me and nobody else, but there's this assumption that having a larger L is in some way better, right? That being detectable or having detectable technologies for longer in some way is equated with survival or with success, and that having a shorter L could be equated with failure. But I'm not sure that's the case. I think we can build technologies that outlive us, or we could become a society that doesn't emit any technosignatures. And so I'm curious about your thoughts there, because I do think there tends to be this idea that bigger L is better, and that's what we should be working toward.
Nadia, can I share my screen again?
Sure.
All right. I'd like to go back to that slide that I just showed very rapidly earlier on, because this is illustrating a little bit what you're saying. I don't think that the size of L means, you know, anything in particular. I mean, the shorter L, as long as it's because you're surviving, it's probably a very good thing. You know, here in the Drake equation that's to the left, you see L to me is a point in time, a very important point in time for a civilization, because it's a time of awareness of its position in the system as a coevolution. Then you have to make a decision whether you ignore that you are in the system, and then your L might be very short. I mean, look at us from the time of the Industrial Revolution to now, it's 150 years, and we are at the tipping point climatically, where we might be just actually killing the environment that's favorable to us, which is also where I would like to, you know, add a footnote. The planet itself is in no danger whatsoever, okay? Life has, I mean, the Earth has been changing throughout the eons and will continue to do so. It will reset to a new equilibrium where humanity doesn't have a place in it, or if it has a place in it, will be not as good as it is right now for quite some time. So it really depends on what you do with the awareness you have. Either you ignore it, you are going to follow the red path, or you are paying attention to it. And then there are a number of different paths. I don't mean that, you know, there are only two, but one is exactly what you said. It is that all of a sudden a civilization becomes invisible because it is so well in symbiosis with its environment that it is undetectable from anything else. And this may happen sooner rather than later. So I don't think that the L factor is something. If tomorrow we realize that we need to get in tune with our environment, and we start developing the technology to do that, we might disappear from visibility within 100 years. I don't know, I would hope so. And we might disappear as well because also willingly, we are developing technologies. We are geoengineering our planet so that we are becoming invisible. Or all of a sudden, we are so advanced and we have so much knowledge of the universe that we discover a new physics that makes us disappear from the radar screen, so to speak, et cetera, et cetera. So I am going to unshare my screen and leave the discussion open here. But there are a number of reasons why I don't think the size of L is really what matters, is what we really do with L, where the awareness goes. We can just ignore everything and the planet is not going to ignore us. Or we can all of a sudden eco-engineer our planet and become invisible for very, very good reasons.
I'll also offer a comment or maybe a caution about equating L, the length of L, with our survival, because it really depends on what you mean by survival. Life, the history of life, the history of evolution of life is all about change and flux and transcendence into new scales and levels of biological organization. And I think we are in the midst of a major transition right now as we see this pace of change accelerating faster and faster. And you just have to look at our technology, which is omnipresent in our lives today. Our portable computers, our smartphones in our pockets, that binds people across the world in a digital web of information that just like that organizational structure of information flow had never existed in the history of our planet before. And I think as technology grows around us, we may end up becoming subsumed in it. I mean, we already are I spend all of my day looking at a screen, whether for work or for play, especially in the pandemic when all of the social interactions were over Zoom too. And so maybe humanity doesn't survive the way we imagine it to survive in the future. Maybe we become engulfed in our technology. Maybe in an analogy to the endosymbiosis between a bacterium and an archaean that created this complex cell structure in the mitochondria that enables us to be around. Maybe our own inventions and the technology that we create end up subsuming us. And you can turn to sci-fi now for imaginings of this happening, whether it's the Matrix or the Borg from Star Trek. But I think this is a very real possibility, and one that we again, the consciousness and the awareness and the self-determination that Nathalie brought up, this is all wrapped into that and our definition of what L and survival means.
I think it's interesting that kind of inherent to this discussion, I've heard it from Anne-Marie and from Bill in his introduction, and also Mike in the conversations that we were having, that energy usage and demand seems to be kind of the crux that's going to tell us where we're going. That's what we have to make some choices around. And so, Mike, when we were speaking earlier, we had talked about some ideas about there being kind of generalizable laws, basically, of metabolism, for biology that maybe you can scale up to cities or societies. And so I'm wondering if maybe we can just kind of go back to that discussion, because I think it's interesting, and it could tell us something about the path that we're on, and how much of a choice we actually have, if this is something that's escapable or not.
Yeah, absolutely. So when I think about the L variable, I first think about some work from Geoffrey West and colleagues. Geoffrey West has been thinking about scaling laws for life, these universal laws that describe things like biological metabolism. And he and his colleagues have shown that the pace of life actually grows slower as the organism grows in size. So you can look at how heart rate changes between something the size of a mouse to something the size of an elephant. And then you can also try to apply these scaling laws to describe cities as biological, sociological, technological organisms of their own. And what you find is that, converse to the way biological metabolism works, the larger a city grows, the more return you get. The greater its GDP, the people earn higher wages, the more patents are produced per capita. People even walk faster in larger cities. And so when you have a law of increasing return like this with size, you actually start growing in a very unbounded way. And so you can see this in how human population has become basically exponential. It's skyrocketing faster and faster with time. And so this work has shown that cities actually have growth trajectories that head towards singularities, which is basically where you increase towards infinite population in a finite amount of time. And this places an extreme demand on energy resources. So West and colleagues claim that we can sort of sidestep these catastrophes that we're heading towards by resetting the initial conditions, by innovating. And we see this with innovations throughout human history since the Industrial Revolution. And the catch is, though, that the singularities come faster and faster and faster. So we sidestep one, we're on the trajectory for a singularity in the slightly distant future, but then the one that comes after that, after we sidestep that one, comes at an even shorter pace. So our frequency of innovations must increase to keep up. And so again, we see plenty of examples of this in this blinding speed of technological innovation. And I think that what I was saying earlier about how technology binds the world together through social interactions that are now completely sidestepping the physical barriers between human beings, the very fact that we can have a conference like this over Zoom with people around the globe, I think sort of indicates that the world as a whole is kind of like a big city now. And maybe our civilization is heading towards a trajectory that is going towards one of these catastrophic singularities where we will soon run out of energy to supply all of the computational and social demands of our way of life. And so I think that we have this very narrow window of time between when we can have the cognitive ability to realize and model the physical trajectory that we are on and the energy demands that it requires, and when we reach that collapse. And that is our sliver of time to, again, make that conscious decision to maybe try to reprioritize at a very fundamental level the dynamics of our civilization away from hyper-capitalistic, exploitative resource gathering and unbounded growth and expansion and productivity and, optimizing GDP to maybe optimizing something else like homeostasis or well-being. And when I told my friend Dr. Stuart Bartlett about this idea the other day, he basically said, okay, so Mike, you're saying all the alien civilizations are either dead because they reached this collapse point and fell over, or they're all just Buddhist monks meditating to prioritize mental well-being. And I think that pretty much sums it up. Maybe this is an answer to the quote unquote Fermi paradox. Maybe this is an answer to what L is, that civilizations either reach this breaking point or they decide consciously to reprioritize what they're optimizing and, in a sense, no longer expand unboundedly into the universe. And that's why we don't see anyone.
That's a very interesting point, Mike, because that goes back to the notion of coevolution of life and its environment, except that, this is a system that fights entropy. But at the same time, if you're becoming a Buddhist monk, there is some sort of, immobilization. So it's just like, we'll have to figure out a balance between the two. But we are at this point. And this is exactly what you're saying. L, maybe it's awareness of our trajectory. The different colored arrows that we are seeing.
Henry, I'm curious about your thoughts as well here, because we are talking, I'm curious.
Yeah, I think I wanted to go back to what Michael said earlier, that, L might not be a fixed number, and, there might be a range. And in terms of an astronomer who's out there, looking for things out there, I wonder if there's a way to sort of find those Buddhist monks, right? Like, can we find the civilizations that have the large L? And if so, how do we do that? Is there something specific we should look for? Or is there some, signal that will show us the difference between a civilization that's hitting that tipping point and going to disappear, or something that has lasted long enough? Or are the ones that last long enough the ones that are hiding from us because we're just not very intelligent at this point? So many questions that we don't have answers to, obviously, but I think it's important to keep looking and to keep enlarging our sample size as much as possible, so that potentially, we can learn something for ourselves as well. If we find something, what can we figure out about how those long-lasting, those large L civilizations, what have they done differently from what we're doing now on Earth? And are we intelligent enough on Earth to actually, learn from that and make a change? I think that's one of the most challenging parts.
Yeah, that makes me think of something that Nathalie had pointed out when we were talking, which was that if you look at the Drake equation, the variables toward the left-hand side, life is just kind of a passive passenger. Like, we don't have a lot to say about the birth rate of stars or how many habitable planets there are in a system, but that as you move toward the right-hand side, we start having the ability to make choices. We can, in a sense, determine, our own L. We can think about whether we want to make technologies that announce our presence, which we've obviously already done. And so I think when I was speaking with Nathalie, she was saying that L is actually empowering. It's a variable that we have control over. And I'm curious, before we open it up to audience Q&A, what do each of you think our options are at this point? When you think about the decision tree that we're looking at, what's left? What can we do?
Well, I'll take a quick answer to that. I think that we see every single year the difference it makes, the fact that we're doing nothing. At this point in time, there is enough energy in the system that it's building up on its own if we are not removing it. So it means that within it's not going to happen in 100 years. It's going to come at us a lot faster than that. It's not a matter of the next generation, and we don't care because, the children of our children are going to have to deal with it. We are going to have to deal with it in a lifetime. We already have to deal with it. And what I'm talking about is the fact that some of our favorite activities won't be necessarily possible anymore because the temperature is too hot most of the year to do things safely, for instance. And this is probably when it's going to hit people, that they cannot go and see their favorite soccer game or football game at some period of the year just because it's too hot or too unsafe for players to be playing. Unfortunately, it's going, when people are being hit in the things they like. Right now, it seems that they don't care. They still can use their car, etc. Oh yes, it's a little warmer in November. Fine, we have spring temperature in November. This is, that's nice. It's a lot better than to be freezing, but it's not normal. So I'm going to leave it here. But what we need to do, we need to do it yesterday. And I think that all of us here, we have, working with space and planetary sciences, we didn't talk so much about this, but there are many of the instruments and the technology that we are using to very, very fast, reach objectives to understand how a planet behave, or what is the habitability of a planet, etc. There is a lot of that technology that we can use to look back at our own planet and support the effort to monitor that change and forecast it and help humanity.
Mm-hmm. Mm-hmm.
Yeah, I'll just, leap onto something that Nathalie said that was very brilliant. She mentioned the word entropy, and I hope not to get too technical with this, but I think that when we use resources internal to our own planetary system, such as fossil fuels, this chemical gradient that we utilize will raise the entropy of our own system when we dissipate that gradient. So that means that the disorder and the heat of our planet is going to increase. We do, however, have a source of low entropy coming at us from our star. So solar energy is external to the planetary system of Earth. And if we utilize that, that will not necessarily raise the disorder of our own world to the degree that burning fossil fuels will. So I'll just throw out a pitch there that we should be really taking solar energy a lot more seriously than we are right now and expanding into that as a green energy source.
Agreed. Anne-Marie?
I also think, it's a different area, but, we need more time to kind of let our own species evolve. Where we tend to operate as individuals on short time scales. We live in an era of cheap thrills. What do I want to do? I'm gonna drive my car today because I feel like it, rather than thinking long term. And so in some sense, I've always thought, we need to buy more time somehow. I think if ultimately we're able to find or even make contact with other civilizations out there, it's just going to be this incredible transition. But the question now is, are we actually going to last long enough to make it there? And so in some sense, we need to figure out a way for human brains to evolve to the point where they have slightly different priorities, and then we make the discoveries, and suddenly something sets in that we need to change the course of humanity. But yeah, the question is, are we going to get there?
Well, Mary, you point a great, you're saying something great here, is that we need to change our first priorities. To need to change our priority from individualistic to thinking of ourselves as, excuse me, as an organism, as one. We are, that goes back to the Carl Sagan pale blue dot. We are all of this, together, and we need to respond together to this crisis, because just like the pandemic, if a quarter or half of the population is not doing it, then what it is worth it. I mean, we don't react for many reasons, socioculturals and because of boundaries, etc. We tend to react as nations, as individuals, instead of thinking as planetary citizens. And I think that how we are going to evolve towards L is this awareness of our planetary citizenship, and we're not there yet.
Bill, I don't know if you've been monitoring the Q&A. I see Jill has her hand raised, so maybe we'll start with Jill, and then if there are questions you want to throw in from the Q&A, we can go there next. I don't know how much time we have left. So
I have. So we're going to, because we had the technical delay at the front end, we're going to go ahead for another 10 or 12 minutes. And I do have some great questions, but I also noted Jill's hand up. So why don't we let Jill start, and then we'll go ahead with some audience Q&A.
So thanks, Nadia. Thanks, Bill.
Sure.
I've always wondered, we think about the distribution of L out there, and we think about it as the number of civilizations with a particular L, and we think about it as monotonic. But what if it's bimodal? And what if the thing that determines whether you are in the large number of short-lived civilizations or you make it over to the cluster of long-lived technologies is whether or not you detect the presence of other technological civilizations?
that's cool. Who wants to respond to that?
That's an interesting, case study that goes back as, how many of us are out there. So then you have to think about, it's an enormous question, Jill, because you have to go back, the distribution of life, and then if are we synchronous in space and time? Is the apparition of life the kind with which we can communicate? Is it generational? Some people say there is no reason it should be generational, because the stuff that makes us has been being produced by stars a long time ago, but also because of its long history, maybe there are many filters, and maybe we are all coming together at this point in time where life is evolved enough that we are getting to the point of being technologically sentient. But so if that's the case, and we are all at the same level in the universe, then it's a little difficult. Then you have more chances to have a regular bell-shaped curve. If you have very old civilization, that's a very different thing. Maybe ET landing on the White House lawn is going to make a huge difference. You know, oftentimes these days, I'm really hoping for this to happen because we need some help. But again, you know, let's not go there, because I think that we really need to help ourselves first and not wait for ET to bring the solution. But yeah, no, it's a loaded question, because it depends so much on, you know, how many of us are out there and what are the different stages we are in. If we are all of the same age, then it's going to be a different question.
I'll just say that, Jill, I love that thought. It never occurred to me before that, you know, discovering other instances of technological civilizations out there would so greatly impact the probability that you wind up having a very long L. I guess I often think about instead the similar question about the discovery of, say, microbial life on other worlds, perhaps in our solar system, or evidence of its presence through the metabolic gases it puts out on an exoplanet that we can detect using telescopes, and how that will change the fabric of our society and the way that we see ourselves and our place in the universe. And I think you're absolutely right that if we end up discovering another technological civilization out there, it will change our mental state as a civilization and influence the trajectory that we're on, hopefully. How it influences exactly is I won't dare comment on, but I think the plausibility of the argument that you laid out is quite high.
Great. Thank you, Michael and Nathalie. And Nadia, I'll go ahead and start with some of the audience questions, if that works.
Sure. Yeah.
And actually, Michael's comment just now was a good segue into the first question that came in, which are, what are some of the signatures of non-human life? What are some of the signatures we might look for that might not be technological in nature that are part of the SETI and astrobiology endeavor?
I can take this one if you want to. I was mentioning the very first one was really the change in our atmosphere. And the oxygenation of the atmosphere of Earth that's directly related to cyanobacteria. That was an immense change in what was happening before before life was able to take some of the carbon from the atmosphere and produce oxygen. I think that life was not so visible, but all of a sudden, 2 million years ago, you have this immense flux of oxygen, and our atmosphere has changed forever. So if anybody had been watching the Earth at that point from afar, they would have started to ask questions about what's going on, because there is a massive disequilibrium all of a sudden that you have to explain. And this is, you know, one of the main things that we are looking for, disequilibria in a planetary environment. That would be one of the things. And disequilibria can be related to many things. It can be related to environmental change. It can be related to biology. But this amount of oxygen in our atmosphere, in this amount of time, they would have had to look for a good reason for it.
Right. Yep, absolutely. And of course, in the field of astrobiology, as all of our speakers know, is constantly looking for a means of identifying biosignatures. In other words, how does biology impart a fingerprint that could be detected, for example, on its planetary atmosphere, or in other ways manifest in such a manner that we could detect it from great distances without necessarily having instrumentation on those worlds. So that's definitely related. I have a specific question here from Ryan, and I think this is really addressed to Anne-Marie. And that is, how distinctive is the transit of an alien megastructure for energy collecting, for example, on its star's light curve? I mean, how does one observe a phenomena like that and come to the conclusion that this might be an alien megastructure of some sort?
Yes, so it really depends on how big that structure is and whether it's in a distinctive shape. So it's certainly possible to have structures that would be difficult to distinguish from, say, transiting planets. But what we're envisioning now is something that's large enough that it seems like it could be too big to be a planet, or something that is not circular at all. So for example, we have a student in my group who's running simulations of all kinds of strange shapes, like a series of triangles, for example. And what would that look like? So the shape of a transiting planet is pretty distinctive. You know, it has an ingress and egress and then kind of a flatter bottom. Triangle wouldn't quite look like that. And so we have to use very high precision facilities to be able to distinguish those shapes, often space telescopes. But yeah, again, it really depends on the nature of the structure. The sort of original canonical Dyson sphere would be something that's almost surrounding the entire star to use up to collect so much energy. If you surround the entire star, you don't see anything at all, right? Do you have a Dyson swarm, numerous panels going around? That might also be distinguishable from a single planet. But right now, we're kind of limited by our own imagination. So time will tell, or not.
And we can also be challenged by toddler meltdown at sometimes, which is something that even our most advanced technology can't really deal with.
Apologies for background sound. It's early.
What makes us human. Anyway, Ryan goes on to ask about what kind of limits will a non-detection place on the existence and scale of such structures. And I think that segues into a point that David Grinspoon makes, where he notes that if we don't find such structures, it might just mean that intelligent civilizations find a way to balance energy consumption with energy renewal and don't need such structures, or put differently, that intelligent species may behave intelligently. What are the comments on that? What are our hopes of behaving intelligent?
That makes me think of what Michael was talking about, the two endpoints. So maybe you want to take that one.
Yeah, sure. I think that's a great point, David. It plays into the hypothesis that I put forward, again, very, very speculative, of course, that maybe civilizations do end up either not learning how to strike that balance, that homeostasis between energy consumption and energy intake and usage, or they do, and then they don't require this grand expansion out into space, reaching type 2 or type 3 civilizations, and that's why we haven't seen evidence of extraterrestrial life visiting Earth yet. So I think that's a really good way of phrasing it.
Wonderful. So another question or comment and question that came up brings up an interesting point, and that is that if younger generations are a little bit more, say, aware of and focused on sustainable energy, responsible technologies, for example, potentially bringing us back into balance with our ecosystem. If we continue on this path, do we think we continue on this path? Does that give us more optimism on our L variable, for example? What are the comments and thoughts on the outlook?
Who wants to pick up the 8 ball?
I don't see anybody like over brimming with optimism here, but certainly I think it's if anybody's going to help us move in the right direction, certainly it's the younger generations.
Yeah,
right,
I think we have to help ourselves, Bill. There is this myth where aliens show up with great wisdom and all of a sudden show us the light. It's at some point, I tend to compare our civilization to a teenager, with enough brain to develop interesting tools, but not enough to understand the consequences of, what can happen when you're playing with them. And unfortunately, I would say that bad experiences is part of the experience. This is how you learn. But the problem with L is really, how much time do you have to learn when you are dealing with a planetary system? And so I think it is time for us not to wait for granddaddy to show up and, tell us what to do with our planet, but a way to be sustainable in the future with great expectancies of L duration is really to learn how our planet behaves and how we should behave with our planet.
Wonderful. Catherine Denning noted that human civilizations have historically seemed to wobble between cycles of partial collapse and then resilience and then rebuilding. So it's not as though we've had this sort of continuous trajectory of progression, right? And so she wonders if societies can in fact wobble for a long time without fully solving their problems or threatening their L variable. Although she notes that sometimes if this wobble happens with increasing instability, things get a little more dicey. Any thoughts on this cycling between, collapse, resilience, and rebuilding?
I guess I'll take that one. So yes, indeed, there are certain parameters or metrics of civilization that go up and down with time. But I think that the ones that are really important in terms of, say, the population of the globe as a whole, and therefore the energy demand and the resource demand that we as a civilization require to keep going, is just monotonically increasing and accelerating at an ever faster pace. I'll just go back and cite some of Jeffrey Russ's work again, where he shows that cities actually do kind of just stick around forever. There have been very few cities that have died or disappeared from the face of the earth. Even if the nation states or the governments or the people in charge come and go, cities have stuck around for a long time. And this is mainly due to the fact that they have this superlinear scaling where they have increasing return with increasing size. That's autocatalytic feedback. It's a positive feedback that keeps them going. And so we may be, again, reaching a state where we can see our global civilization as one big city. And then what does that mean for our trajectory? It could lead to some kind of collapse unless we make that conscious shift in the fabric of our society.
Wonderful, thank you, Michael. So we'll close with one question and ask maybe each of you to opine on this very, very quickly so we can keep on track here. But that is, how can we make politicians aware of the L variable and what the L variable has to offer in terms of bringing a different context and perspective to this question of climate change? Is there any hope? Well, one way might be to invite the politicians to the spring event that we're going to have to continue this conversation.
I guess, it's politicians are going to be, they are worse than most of people because it's only when they won't be able to do anything else that they are going to react. Right now, we're seeing some goodwill with different organizations and committees and climate, and people are speaking louder and louder. The problem is the distribution of power, and until that we cannot fight the power of money with fossil fuels and other things, and the power that's related by having your hands on these resources that make the world go around at this point in time, is going to be really difficult. But I think it's a matter of raising the awareness of more and more people. It's a grassroots work, and but it has to happen fast. In terms of politics, we need to do the things that we are doing right now. Scientists need to speak out. Politicians, we're already seeing the light, needs to speak out. We need to educate the young kids because they are coming as a blank page. If we're telling them to use in the future green resources, to behave like planetary citizens instead of individualistic, entities, then we can change everything very, very quickly. And it starts with the children.
Great. Well, I think that's a wonderful way to wrap up this discussion. I will say that, I hope I'm going to pronounce this right, but Sivara Makrishna has noted that the B-deloid rotifer survives for 24,000 years frozen in Siberia. So maybe there are some lessons we can learn from B-deloid rotifer going forward. But in the meantime, I want to thank Nadia and Michael and Nathalie and Anne-Marie. Wonderful panel, great discussion, great questions from the audience.